Today, let's talk about potential energy. Now, we're just talking about gravitational potential energy, because there is spring potential energy, which will be a topic for another day. Because you have a bright idea, Zach. All right, so you can jot these down if you like. Of course, I'll be posting a little bit later to Schoology. Hopefully Zoe's following along online, no doubt. That's probably one of her #1 things to do in Toronto, is follow along physics class. So, vertical work and potential energy. Now, you've seen some of these formulas already, so none of them are going to be a big, giant surprise. But we're just going to sort of talk about things a little bit more in depth. The only way for me to cover things up was to do this. So.
Wow.
You guys are hilarious. The work done in lifting a mass a vertical distance d, or h, whichever you prefer, h for height, of course, d for distance, is stored inside the body as increased potential energy. Okay? Now, for whatever reason, U is the letter for potential energy. I don't know why. The convention for kinetic energy seems to be Ke or Ek, and so you would think that we would use Pe or Ep, both of which are perfectly fine with me, but for some, I don't know, for some reason, well, gravitational, UG, UG, yeah, not Eugene, UG, or just, I mean, I guess if it was spring potential energy, well, then that would be US. So I just sort of throw that out there because you might see that sometime in the future. I don't know.
Why draw V?
I just drew it poorly. Alrighty. So remember our old friend W equals FD?
Wait, why?
Since the F is equal and opposite to the weight force. So when you're lifting something, the force that you require is equal to the weight force, which is equal to mass times gravity. We're going to go with D being H for height. It can remain as D if we want. So FD simply becomes mgh. Potential energy mgh. Or mgg is fine too. Mass times gravity times height. The higher it goes, the more potential gravity it has, right? Or potential energy it has, right?
What's that terminal velocity?
Does that mean something taller has more potential?
Their head does.
Okay.
Are we gonna you have to incorporate terminal velocity?
No. Yeah, it takes a lot of mass.
He has a big head.
Moving on. Okay, so let's look at how potential energy and kinetic energy change as the object moves or it falls in the Earth's gravitational field. So here I have a 5 kilogram mass, and it's about 8 meters in the air. How much potential energy does it have? Well, 5 times 9.8 times 8, it has about 392 joules of potential energy. Right? Now, as that thing falls, the total energy should do what? Total energy. Well, how much, I guess that's probably the next question, is how much kinetic energy does it have?
Zero.
Zero. It's sitting on a ledge.
Oh.
It has 0 joules of kinetic energy, right? Can I make these bigger? I can. Which tells me that the total energy is 392, right? Total energy is 392. Is that 392 going to remain the same throughout the fall?
So we actually have to figure out total energy ever. Potential energy.
We just did off record.
I know, but it's potential energy plus kinetic energy.
Yeah.
But if something's moving, wouldn't it not have potential energy? So like things still would have kinetic energy.
No, it can have both, right? Well, as it's falling, as the stack of Post-its are falling, right? It's moving, so it's got kinetic energy, but it's still got more to fall, so it's got potential.
Those potentials going down.
Right? It doesn't lose its potential until it
It's gone.
Are we
hits
not gonna, like,
relative ground.
have an equation where we find out like how much potential energy it loses on the way down?
It would be exactly 392.
Yeah, like
Because when the ball gets to the bottom here, right, it's going to have zero.
Stay the same, like, with unit areas.
Yeah, you're right. There's a little bit of energy that's lost heat, the heat, yeah. Friction, right? Okay. So we're good?
Okay. Why is kinetic energy?
It's at rest. It's not moving.
Oh, UK and the other is U.
I don't know. It just is. It's one of the mysteries. One of the mysteries of mankind.
That would be like W.
Okay. So what I did here was I just so it's all on the same page, I just sort of copied that. You guys can ignore that up there. So now, when it's at a 3-meter height, I think it's 3 meters, is it? Yes, it's 3-meter height. How much potential energy does it have? 5 times 9.8 times 3. Now it's got 147 joules, still potential energy. How come it still has potential energy? It's still got 3 meters to fall. It's still falling.
So when it gets to ground level,
It would be 0, the potential energy, right?
you have to like convert
And the kinetic is also zero.
After it stopped, right?
Do you have to convert all that like sea level stuff, like at sub-zero? Because if you're on a mountain,
Yeah, it's all relative, right?
relative to
Relative to what you consider to be the bottom. Yeah. Yes?
what happens if bouncing back up?
Good question.
Can we do that?
Yeah, well, no, but we could talk about it. If it bounces back up, in fact, when a ball bounces back up, that's a pretty good indication.
Wait, if it's going down, would your kinetic energy be negative?
Yeah, it would be negative. Well,
Is it like a vector?
It's the old tennis ball.
no, I don't think it is a vector. It's a good question. I don't think it is a vector.
If it bounces up, then it would be positive.
Yeah, I mean, I guess it could be, right? So if I drop it from a certain height, the tennis ball, it should theoretically do what? Bounce back to the same height, conservation of energy. And the reason it doesn't is because some energy is lost. It compresses the ball when it hits, right? And then it releases it. I mean, if I had a thermometer or some type of measuring device that was precise enough, accurate enough, it should be hotter now, right? Because it generated some heat when it bounced, right? And that energy is lost, which is why eventually it will.
It bounce back like half every.
You could probably work out a sequence, yeah. Right?
Do it as we do
Well,
right
like if the ball's going up, is there any way you can calculate the potential energy?
Well, it would.
Get bigger.
Yeah, the potential energy would grow as the kinetic energy goes back to 0, right?
Does that be questions like?
I guess it could be. Yeah.
Is all the-
You would have to know how much energy is lost. I'd have to say something like 20% is lost every time it bounces, right? So, like, if we were to do that, okay? So, if I said 20% is lost, that means it should have 392. So you would just take 392. I guess you'd multiply by 80% because that's how much is left over, right? And you'd have 314. You'd have 314 joules after, and then you could actually figure out how high it would go, couldn't you?
I guess you can. All these potential energies are all like instantaneous conditions.
Yeah. Okay, now what I'm going to do here is I'm going to figure out how fast it's going. Okay, so I'm going back in time a little bit here. Vf squared is vi squared plus 2ad. The initial velocity was 0 up here. Right? Now, how come I used a 5 right there? How come I used 5 and not 3?
8 minus 3.
Yeah, because the 3 is the height. How far has it been accelerating? That distance there is 5, right? Okay, so I used 5 because it's fallen 5 meters. I determined that it's traveling at 9.9 meters per second. What kind of kinetic energy is that? Using our new friend from yesterday, EK equals mv squared over 2. That's the kinetic energy. 5 times 9.9 squared divided by 2 gives me 245 joules of kinetic energy. Zach, put the phone away. 245 joules of kinetic. Now, if I were to add those two together, which I'm likely to do underneath that gray box, what number should I get?
Well, you just add them together.
What do you know? 392. How come? Because energy must be conserved. Now, you might be off by a little bit due to rounding and what have you, but for the most part, energy should be conserved. In other words, did I really need to do those two things? Or did I need to do this one to get the kinetic energy? No. All I have to do is,
Minus that.
all I gotta do is subtract, right? 392 minus 147. All I have to do is subtract.
It's kind of expensive.
Good, good? Okay, I'll pause for a moment. All right, so the last little bit here, you will see that I've got, on the left-hand side, I've got delta U, which would be the change in potential energy, UF minus UI, final minus initial. So I went from, I ended up at 147, I subtract 392, I lost 245 joules of potential energy. Oddly enough, not oddly enough, it's not odd at all. In fact, it's exactly what you would expect. I lost 245 joules of potential energy. I gained 245 joules of kinetic. No big surprise.
So if it's a question, always uses like conservation of energy. They should always be equal.
This should be equal, yeah. Should be equal. Moving on, 7. Note, total energy is the same at all times. There is conservation of energy. And as an object moves, the changes in potential and kinetic energy are equal and opposite. Do we need to write that down?
No.
It's pretty
Pretty straightforward. Total energy remains the same, and the changes in the two are equal and opposite. Give me that. Give it to me.
What is it?
Okay, let's have a look at some sample problems. Alrighty, so here we go. Rocky, the 1 kilogram flying squirrel. Rocky is a flying squirrel. Bullwinkle, of course, is a moose. He does not fly.
Sometimes.
You try.
He is initially up 10 meters up in a tree, and then he jumps to the ground.
Why is he doing that?
It's a cartoon. Don't worry, he's a flying squirrel. He's okay. The total energy at the start, which of course is the total energy at all times, and his velocity after he's fallen 6 meters, which is 4 meters from the ground. Well, now flying squirrel is a bit of a misnomer. He doesn't fly.
And they can lie.
All right, now this looks awfully like the sample ones that we just did, is it not?
Kind of.
I think so. So total energy at the start, U equals mgh. He's 1 kilogram, that's nice. 9.8 times 10 meters. Hopefully no one's pulling out a calculator. Go 9.8 times 10.
They can draw it.
I think it's 908.
I think it's 98, Jordy.
98, Jordan.
98 joules. Now, what's his velocity after he's fallen 6 meters, which is 4 meters from the ground? So there's two ways that you could do this. Let's do it sort of from a conservation of energy sort of way of thinking. So if he's fallen 6 meters, then he is actually 4 meters from the ground. So I'm going to go U, I'll put a little 4 right there to indicate at the 4 meter height. So that would be 1 times 9.8 times 4. Because I'm finding his potential energy when he's 4 meters from the ground, right? So 9.8 times 4, I think is, well, maybe I'll have to actually, 39.2, right?
I'm not sure.
39.2 joules. So what happened to all the rest of it? It's been converted to kinetic energy, right? So I'm going to say something like ET is equal to U plus EK. Yep, total energy. The total energy was the 98. The potential energy is 39.2. Find how much kinetic energy he has when he's at that height. So 98 minus 39.2 is 58.8 joules of kinetic energy, right? And if I want to find its velocity, now I'm going to go EK is equal to mv squared over 2. How much kinetic energy? 58.8. Mass is 1. Find the velocity over 2. That's squared. V is 58.8 times 2 and square root. You'll be traveling at 10.8 meters per second.
And it does find the velocity, but do we need a direction?
I guess technically it should be down, shouldn't it? Right?
Negative.
Yeah. Now, can you make the math work so that it works out to be negative?
Yeah.
I don't think so, because you're going to have v squared here, right? Like, it doesn't matter what you do, you're not going to end up with a negative.
Yeah, because if there's a negative inside of your square root.
Well, you're right. Technically, the square root of 2 times 58.8 is plus or minus 10.8, isn't it?
10.8 meters down.
Yeah. Yeah. I mean, the negative doesn't always come out of the math. Sometimes you have to assign it.
What?
What is that? It's the guy! The guy's there. Hello, hello, guys. That's the reason that is. I didn't read it.
So anyways.
A 2 kilogram ball.
On Sunday!
Two.
Medora!
A 2 kilogram ball. A 2 kilogram ball is launched at ground level 50 meters straight up. Find the total initial energy. Find the height of rise. You can figure out how high it's going to go based on the energy, the velocity. You can find the kinetic energy when it's risen halfway off the ground. You can find how fast it's going when it's risen 100 meters off the ground, and so on. Lots of different things. All based on conservation of energy. So the first thing you need to know is the total initial energy, which I will label EKI. Now, yes, some of you might want to say it's 0, but what I'm talking about is at the point when it's just launched at 50. So prior to launching, yes, it's 0, but then immediately following the launch itself. So 2 times 50 squared, that's pretty fast. Divide by 2. 2's cancel. 50 squared. 2,500 joules of initial kinetic energy.
That's a lot.
Yeah.
Crazy.
Now, to find the height of rise using the energy standpoint, if the 2,500 joules is how much it has at the start, right? When it's right up here at the peak, how much potential energy is going to have right at the top? 2,500, right? All of that kinetic energy must be transferred to potential. So in other words, all I really have to do is go U equals mgh. All of that 2,500 becomes potential. So 2,500 is equal to 2 times 9.8 times my height. And I get a height of 127.6 meters. That's pretty easy to do. I want you to think ahead here, because part C asks for the kinetic energy when it's risen halfway off the ground. In other words, when it's halfway to 127.6, which is that, about 63, something like that? 63 point something. Is it going to have half the energy? It seems like it should, doesn't it? Like if it's halfway up, shouldn't it have lost half its potential and gained half its potential and lost half its kinetic? Well, let's just see. Let's just see. So my new height is going to be 127.6. Divide by 2, which of course is
64?
64.3.
63.8, I think, isn't it?
Oh.
63.8. So how much kinetic energy does it have? Now, What do you think we should do? I could figure out, call a friend. I could go MGH, right? I can find out how much potential energy it has, so that's going to be 2 times 9.8 times 63.8. Shouldn't that just be like half? Pretty sure it should be 2 times 9.8 times 63.8. 1250.
No, kinetic would be also.
Exactly, right? Therefore, the kinetic must be, I'll just show it just for the sake of completeness, but I think we all know that it's going to be also 1250. So that's sort of intuitive. That sort of makes sense. Right? Is it going to be going? Now it doesn't ask this. Maybe I should ask this question instead. What's actually the question? You know what? I'm going to skip D, and I'm going to change D to velocity when it's risen to this point. Is it going to be going 25 meters per second? Halfway. Should it be going half the speed?
Yes.
I don't know.
Well,
Quarter.
EK mv squared over 2, 1250, 2v squared. Do you have a funny feeling that v squared is going to mess things up?
Yeah. Inverse proportional crash. 35.35. Wow.
Interesting. It's because it's squared, right? It's v squared. Yeah, it's not a direct relationship.
So slowing down.
Well, it is. It's gravity's right. It's slowing down. It's not a direct relationship. Okay. How about you guys try? I'll let Stefan go to the bathroom, and I will ask you to give number 3 a try. I'll have to draw a picture for it too, I think. For it. You guys try number 3. There's lots of room.
What? Like that.
Okay. So we got a 3 kilogram mass. It's rising upward at 30 meters per second. It rises to a maximum height and then lands on a 5 meter height ledge on the way down. Find the total energy, find how high it goes, and find how fast it's going when it hits the ledge.
Okay. So.
Give that a try. All right, total energy. Total energy at the start is all kinetic. mv squared over 2. So that's going to be 3 times 30 squared all over 2. 900 times 1.5.
No, it's a height.
1350, right? Did you get 1350?
Yeah.
Okay.
Now do the next one.
Okay. The maximum height of rise. So the maximum height of rise, that occurs when
U is equal to
Potential.
all of the initial kinetic energy is transferred to potential, right? So MGH, so 1350 is 3 times 9.8 times my H. So 1350 divided by 3, divide that by 9.8, 45.9 meters. How am I going to do part C? Well, we could find out how far it falls. We could use VF squared equals VI squared plus 280 that way. We could use that, but I'm liking this energy kind of thing. How about if I go, the potential energy at a height of 5 is going to be 3 times 9.8 times 5 is 147. So it should have 147 joules of potential energy when it's there, which means therefore it should have how much kinetic?
1350.
It should have 1350 minus 147, right?
1203.
1203.
Yep.
It should have 1203 joules of kinetic. And now we're going to go mv squared over 2.
That was a lot more work.
You think so?
Yeah.
Then what? Then find, I guess, but you'd have to know, yeah, well, it's the same thing. You'd have to do a subtraction, and then I think it's exactly the same. It's 2.
I like this way better just because.
Oh, yeah, you're right. You'd have to do this, I guess, yeah. I guess you're right. Okay, so 1203 times 2 divided by 3, and then square root.
28.32.
28.32. 28.3 meters per second. All
I
right.
like doing it that way though because it's uniform.
I suppose, yeah. Alrighty, I'm going to stop talking because that's enough of me. And you got two, well, you can, those of you that were away yesterday should get the sheets from yesterday. Here's potential energy. Seven problems there, is that right? Should be 9. Oh, there's 9 in the back. Oh, there's 2 pages worth.
What was it, 1300?
Good for you, Zach.
Whoa, that was cool.